Okay, hi everyone. This is Dan Barry, and I'm pleased to welcome you to the new season of the MAP webinar series for 2015 and 2016. Thank you for joining. We have a webinar today on the topic of the California drought, and we're going to explore both the implications of El Nino, the current ongoing El Nino event, as well as get an operational update from CPC. So we have three speakers, and the first will be John Gottschalk from CPC. He's going to give an operational update, and then we will hear from Richard Seeger from Columbia University, who's going to talk about the drought and the implications of the current El Nino. And then finally we'll hear from Andy Howell, who's at the Earth System Research Laboratory, NOAA's ESRL, and he's going to talk about whether El Nino intensity matters for California precip. And the last two talks will be very complementary. They're dealing with some science that was recently published in a brief scientific assessment by a subgroup of the Drought Task Force led by Richard Seeger, and you can get a copy of that on our website at cpo.noaa.gov/map/CaliforniaENSO, if my memory serves me correctly. So, Richard, are you on the line? Or, sorry, actually, John. John, you're up first. John, are you on the line?
Yes, I am.
Okay, great. So, John, I'm going to switch control over to your computer, and you can share your screen with us, bring your slides up, and take it away.
Can you see my screen okay?
Yeah, it looks great.
Okay, great. Okay, thank you very much. Everyone, good afternoon or good morning, depending where you're at. Dan asked me to give a brief update on some of our latest forecasts. I will start with the latest ENSO outlook, but also discuss the most recent seasonal precipitation and drought outlooks. So I want to first do that by taking a look at some model SST predictions first. These are just two spatial maps here, one of seasonal sea surface temperature anomalies, October, November, December on the right, and January, February, March on the left. I just want to kind of show the extent. This is very similar for most of the models of above average temperatures indicated by the warm colors from just west of the date line during the October, November, December period to the South American coast, but some of the largest anomalies as much as 2 to 3 degrees above normal. Obviously a very strong perturbation in the climate system. As we move to JFM on the right-hand side, this area is very similar in coverage, although it's less overall, but generally across the East Central Pacific, we start to see a little bit less of the westward extent of the sea surface temperature anomalies during that time as we get later into the winter and into the spring. If we focus on some very specific areas in the Nino 3.4 region, basically a very climate-sensitive region for the mid-latitudes, one of them. I want to first show some predictions of that variable Nino 3.4, which is generally a box average in the East Central Pacific. And what's shown here is the latest CFS forecast. As you can see, we've had an increase in temperatures. The black line is the observations. As we go to the right-hand side of the figure, you can see the forecast from the CFS from a number of different members. The dashed black line is the ensemble mean. And what this basically shows is just this is a PDF and spread-corrected version of the CFS, and basically has a peak of during the October, November, December season, generally flat here as we move towards the late fall into the early winter, and then we see a decrease in the mean and in most of the ensemble members as we get towards the later winter months to just about near 0.5 in the ensemble mean by the April, May, June time period. If we take a look at some more forecasts from the mid-September 2015 plume from IRI and CPC, shows a very similar sort of pattern with a peak during the late fall months into the early winter and a decrease as we move towards the spring. The only thing that I would add here is that some of the models have a little bit later peak than the CFS, maybe more in the November, December, January period, but generally during the late fall and the very early part of the winter is what we're still going with the peak in at least the SST realm. And finally, for those interested in North American multi-model ensemble, very similar sort of evolution. Again, these are on the x-axis is time as you go to the right, increasing in time, and the anomalies are on the y-axis, similar to the other two figures. and the dotted line is the North American Multi-Model Ensemble mean, which also shows a peak during November and December time period. So they're all indicating this general peak in the SSTs during the late fall and winter with a decrease moving forward. So with that information plus the ongoing observations that we see with the warmer SSTs, as well as the strong coupling that we're seeing in the atmosphere, both in the circulation and tropical rainfall across the central and eastern Pacific, the official forecast from CPC hasn't changed much in the sense of the probabilities, still favoring greater than 95% probability of El Nino, of course, through the January, February, March period. The red bars are El Nino, the green bars are the neutral phase event, so time increases as you go to the right, probabilities on the y-axis. What might be a little bit different here is that we have as we're getting further now into the spring months with the outlook, we see a decrease in the probabilities for El Nino down to about 55% by the April, May, June 2016 period, with the probabilities for neutral conditions increasing now to about 40%. This is pretty much unanimous in the sense of the late fall and winter, early winter months for a strong El Nino event. Now turning to the drought, this is the latest drought outlook. This was released in mid-September, about a little over a week ago, and this extends, it's important that this extends through just the months of December 31st, and two main areas to point out, I guess, across much of the West. I'll explain why this is in a second. Generally favoring some drought development to develop across parts from northeast Nevada, across parts of South Idaho, towards much of Montana and the northwest parts of Wyoming. Persistence of drought continuing across much of the Pacific Northwest. As we go towards the south, across the southern tier of the United States, we're favoring the grays improvement, which is the one category in the drought monitor improvement. The green contours are drought removal, meaning we eventually see either D0 or no drought whatsoever. In general, we are favoring some areas of improvement across California, along the coastal areas, and across parts of the southern areas of California, southern Nevada, parts of the interior Southwest where there's more abnormal dryness, or D1, so we have more removal in those areas. We also have improvement and removal forecast across much of the southern tier. Again, as this goes through December, we're expecting to see some more moisture across the southern tier of the United States. I'll show that in a second, from Texas into parts of North Carolina. As far as the latest seasonal outlooks are concerned, this is October, November, and December for precipitation on the left and temperature on the right. A few things to point out, going to focus with the drought areas. In general, favoring a below median precipitation across the northern Rockies, parts of the northern high plains, and the Pacific Northwest. We are favoring above median precipitation from parts of Southern California into the Central Plains and eastward along the Gulf Coast into the southeast. The highest probabilities during this season are across parts of South Texas and across southern Florida. As far as precipitation is concerned, temperature is concerned, favoring above normal temperatures through California up to the Pacific Northwest and across the northern tier of the country, with some extension down across the eastern seaboard, favoring below normal temperatures across some parts of the southern plains and the eastern parts of the Southwest. So some of the drought conditions, as you can see, with below median precipitation favored, as well as above normal temperatures, for some of the reasons for drought development across parts of the northern Rockies, northern high plains, and Pacific Northwest. One of the factors in the outlook for October, November, December, and of course through into the winter, is the ENSO, the El Nino. This is what's shown here. On the left-hand side is just a regression map for El Nino events, and on the right is just a correlation, which gives you a percentage of the somewhat of the confidence and the impact that you see on the left. And you can see in the upper left, again, favoring dry conditions overall during the October, November, December season, with some correlation shown on the correlation map on the right. And for the above average precipitation, we have across parts of southern Alaska and along the southern tier of the U.S. From the Southwest across the Gulf Coast into the southeast part of the country. As we take a look at the remaining forecasts, but before I want to show you some of the forecast tools for October, November, and December. And this is two forecasts from Dynamical Model Guidance. One is the North American Multi-Model Ensemble on the left and the International Multi-Model Ensemble on the right, which includes the CFS, the Meteo France model, and the European Center. And you can see from both of these maps, these forecasts are quite wet. In general, much of the CONUS and the NMME is favored to be above median precipitation. You can see the highest areas are where we have in our forecast for above median precipitation are the models across the southern plains, central plains, and southeast, especially across southern Georgia and Florida, extending to parts of southern California, and also including areas in southern Alaska. The IME has this very similar sort of pattern. The one thing that's absent in these model simulations that we've been discussing is the lack of a stronger dry signal across parts of the Pacific Northwest, both in the North American Multi-Model Ensemble, some of the models, as well as the IMME here on the right. There's a weak signal, as you can see here. As we move through the winter months into the spring, I want to show the series of outlooks that we have from CPC, the latest ones. I've already discussed October, November, and December. November, December, and January is very similar. Again, wet along the southern tier, two dry areas near the Great Lakes region and the Pacific Northwest. As we move into the core of the winter months, generally the highest probability for below median precipitation really shifts to the northern Rockies, as shown here, and then we start to have development across the Great Lakes region towards the Tennessee Valley as we get into the January, February, March period. As far as the above median precipitation is concerned, obviously above median precipitation is favored along the southern tier. A couple main points to bring out: in January, February, March, the highest probabilities with the largest coverage occurs with as much as 60% probability from Southern California across Arizona to New Mexico, and also as high as 70% across parts of southern Florida, where the teleconnection for El Nino, strong El Ninos are the greatest during January, February, March, the January, February, March season. As we get a little further on into time to February, March, and April, you can see starts to have a relaxation in the probabilities and coverage as we move forward. One thing I really want to note with respect to, of course, the West Coast, what's shown here was made available from the Climate Portal. We'd like to thank those folks. These are December, January, and February ENSO El Nino composites. The top two lines are basically the other strong El Nino events from those periods, from 1950 onwards. And I really just want to show this. First of all, this plot here is a moderate event, so don't key in on that. But overall, what I want to point out is that even with these events, there's a high amount of variability along the West Coast. 97, 98, we had basically above median precipitation across much of California. In 82, 83, basically the whole coast. Mixed along the West Coast for 72, 73, actually dry in 65 and 66. Wet on the northern half of the West Coast in 57 and 58, and then the remaining 2 years are actually dry across much of the West Coast with a weak wet signal along the southern parts of California. So obviously, even though we are favoring a strong El Nino event, and we are favoring certainly a decent wet season, above average, we're favoring above average wet season, there's still quite a bit of uncertainty overall, and this obviously has strong impacts for the drought in California and other areas. And the last slide I want to show just is the December, January, and February tools from the North American Multi-Model Ensemble, which is very similar to what our forecasts are. Our forecasts are pretty much based on the El Nino, expected El Nino response that we see in the historical record, plus dynamical model guidance, much of which is shown here. And generally, the probabilities for December, January, and February from the NMME shall focus on that. Generally dry across parts of the Pacific Northwest, Northern Rockies, Great Lakes, with, again, this wet signature. And if you look at the host of models here, there's quite a bit of spread, but they all generally have a forecast that's very consistent with El Nino composites to first order. So with that, I'd like to thank you for your time, and I'll try to answer any questions that there's.
Great, thanks a lot, John. I think that was a nice setup to the two subsequent science talks that we're going to have from Richard and Andy. So thanks for the setup. So for those who are logged in on the WebEx, the way to ask a question, the preferred way is for you to raise your hand in WebEx. And to do that, you want to go to the top of the screen where it says that you're viewing John's desktop. And if you toggle over that, you'll get a participants list. And at the bottom left-hand corner of that participants list, there's a little logo that looks like a hand. You click that, and I'll know you have a question. Alternatively, if you're having trouble finding that, you can send me a chat message or use the Q&A function, and we can do questions that way. So I'll keep my eye out. In the meantime, is there a question in the room for John? Okay, I do see we have a question from Krista Peters-Ladard. So, Krista, I'm going to unmute your phone, and you can ask. Krista, are you there?
Hey, I'm here.
Okay, go ahead.
Yeah, John, I was curious about in the 2 slides ago, there was a linear feature, that one. There's a linear feature on the California-Oregon border in a lot of these. Do you know what's going on there?
I don't know for sure, but these are based on Climate Division data, and I think that's the edge of the Climate Division, but I'd have to confirm that with you probably offline.
Okay, yeah, because it's pretty persistent, like even in the negative anomalies and the positive anomalies, there's that feature. Just,
right.
It's pretty striking. So, okay, thanks.
Yeah, I agree.
Okay, great. Thanks a lot, Krista. In WebEx, if you can put your hand back down, that would be great, unless you have another question. So I don't see any other questions in WebEx at the moment. Last chance in the room here. Anybody have a question for John? No? Okay, so then I think what we'll do is move on to Richard. John, thank you so much for calling in and providing that update.
You're welcome.
Okay, so next up is Richard Seeger, and Richard, I am transferring control over your computer. I also have to unmute you. Okay, you there, Richard?
Yes, I'm here.
Okay, perfect, and we can see your screen.
Okay.
Yeah, looks great. Whenever you're ready, go ahead.
All right. Okay, so this is some work we did as a follow-on from the work the Drought Task Force did. That paper was published by NOAA in December, and then it was in Journal of Climate this month, and then we sort of thought, well, we'd better do some work to go on from that to think about what the current El Nino means for this coming winter. And then we brought in the additional team members from Mingfang Ting and Bo-Ting Zhong, and they're both sitting here with me right now. Okay, so first of all, a little bit of a quick review about how California got into the drought that it is in, and the picture on the left here is from the Drought Task Force report. Well, it's based on the analysis. We didn't show this exact picture, but this is actually an average over the 3 winters from 2011 to 14, so it doesn't include the most recent winter. And you got the sea surface temperature anomalies, the 200 millibar geopotential heights, and then over the United States, the precipitation anomaly. And the common feature here throughout the 3 winters was this ridge of high pressure and dry extending pretty much across the west coast. The sea surface temperature anomalies did vary through these 3 winters. The first winter was a La Nina event, but then it went La Nina, well, ENSO neutral, and in the 2 winters of 12-13 and 13-14, the warm anomaly in the western tropical Pacific there was key. And then the lower panel on the left is what we got from a 7-model ensemble that we used in order to study the causes of this drought. And you can see that it reproduces, the models in their multi-model mean reproduce that ridge of high pressure and dry conditions of the west coast. They're just not quite as dry as the observations were. And some follow-on work that we're doing at Lamont is finding that the tropical sea surface temperature anomalies, possibly actually including off the map here, but some more warm anomalies in the eastern Indian Ocean were key to forcing the ridge. So tropical SST driving was important for how California got into this drought, explaining at least a large part of the precipitation reduction. There was a lot of questions when we published that as to whether temperature anomalies were also important in the drought, and that was in a paper we published in GRL just recently with Park Williams as the lead author. The 3 time series in the middle of this slide show the precipitation from 1900 on for all of California, and you can see there's a lot of up and down, but there's no clear upward or downward trend. But on the other hand, temperatures have steadily climbed, and especially strongly in the last couple of decades in California. And these were combined together with information on humidity, net radiation, and so on into a Penman-Monteith computation of the Palmer Drought Severity Index using all possible combinations of input data, so different combinations of precipitation, temperature to fully cover to create an ensemble of PDSI simulations. And there you can see that the temperature increase did drive a downward reduction in PDSI. So from the PDSI perspective, for the last several winters, about 3/4 of the PDSI depression was caused by the precipitation drop, but about 1/4 was caused by the high temperature. And of that quarter, about 1/4 to 3/4 of that was due to the long-term warming trend, but natural variability, seemingly this same high-pressure ridge, contributed to some of that warming as well. So precipitation-driven, but amplified or exacerbated to some extent by the warming temperature. As I said, the sea surface temperature force models could not fully capture the strength of this drought, and that's no surprise because it turns out that there's only a limited strength of connection between the tropical oceans and California, and this is a composite of the driest 15% of winters that have occurred in California, and actually typically California dry winters are not related to the tropics at all, but seem to be related to a mid-latitude wave train, probably internal atmospheric variability. That's typical winters. Tropical sea surface temperatures do come in and can drive dry winters, but it's just not the normal way that actually happens. In contrast, wet winters in California are more typically associated with wet conditions. So this is the composite over the 15% of wettest winters, and you see the warm conditions in the tropical Pacific there, a trough over the west coast and wet conditions across the wet coast. So in doing the work that I'm going to talk about next, it was building on this kind of relationship to parse this apart in terms of Northern California, Southern California, and how this evolves through the winter and whether there's any sort of nonlinear dependence there. So this is the strength of the correlation coefficient between California precipitation and the Nino 3.4 index for Southern California and Northern California as a function going through the winter. And you can see that, first of all, the connection is stronger in Southern California than it is in Northern California, and also that it strengthens as the winter goes on. The one on the far right where it dips down a bit is the full 6-month winter half year. So it actually strengthens from October, November, December, or November, December, January, all the way through to February, March, and April. And then we also took apart winters that are El Nino and divided them up into ones that were El Nino and wet in California and ones that were El Nino but they weren't wet in California. And this is for the entire winter half year. And you can see that the top two, for the ones that are wet, it's typically the El Ninos that are strong that are doing this. When you get this relationship that it's an El Nino but it's not wet, it's more typically because the El Nino is actually not a very strong event. So it suggests there is a dependence on the intensity of El Nino, which we'll be hearing more about in the third talk. So here we have some composites for the early half of the winter and the second half of the winter, and then for the weaker El Ninos in the top, Nino 3-4 between 0.5 degree and 1 degree, and then for the moderate to strong El Ninos at the bottom, Nino 3-4 greater than 1 degree. So you can see that if what you're interested in is a wet California during El Nino, It's much more likely to happen during the strong events. So in the lower two panels, Southern California reaching up into Northern California wet in the first half of the winter, and then in the second half of the winter, you clearly have the wet anomaly being spread all the way from Mexico up through into Oregon. Whereas in the weaker El Nino winters, in the early half of the winter, there's really no relation in California, and then it's kind of restricted to Southern California in the second half of the winter. So a stronger relationship in the latter half of the winter and in Southern California than Northern California, but a strong event that persists all the way through into the second half of the winter is very likely to make it wet in all of California. That relationship that I just showed you based on observations, and for the heights we were using the 20th century reanalysis, so it goes back to 1900. We can get the same results from the new ERA, that's 20th century reanalysis as well. And then here it is from a 16-member sea surface temperature forced simulation with the vintage CCM3 ensemble, which that's a model we still find the best for simulating North American drought of the NCAR models. And it reproduces this relationship very well. So somehow this is something that is robust within the links between sea surface temperature in the tropical Pacific, the atmospheric circulation, and precipitation. We find it very interesting that if you look at the bottom two for strong El Niños, or the top two for the weaker El Niños, that the teleconnection pattern actually strengthens from the early part of the winter to the latter half of the winter, and with it the precipitation teleconnection, and that's occurring even as the tropical Pacific sea surface temperature anomalies weaken. So that's kind of curious why the strengthening of the teleconnection happens even as the El Nino event starts waning. So John already showed this, but this is the IRI CPC plume of ENSO predictions. If you look at the dynamical model average for this, for the first half of the winter, it's a forecast of 2.5 K for Nino 3.4, and then for the second half of the winter, 1.8 K. So we really are well into the realm of the strong El Nino event in terms of what I've been showing so far. If that February, March, April value of over 1.5 degree centigrade actually occurs, I think that would be a record Nino 3.4 anomaly for that season. And here's the sea surface temperature map for the middle of the winter, January, February, March. John's already shown that, but you can see it's getting up above 3 degrees right in the middle there. Notice that the forecast is that the warm sea surface temperature anomalies in the western tropical Pacific that were key to forcing the ridge for the past winters has gone away in this forecast. So the sea surface temperature great anomaly is very much the reverse of what it's been in the last several winters. This then is a scatter plot, again by early and late half winter for Northern California and Southern California. I've updated these Borting updated these to use a climatology that is the same as was used for the forecasts we just saw, 1981 to 2010. And you can see that in general, there's not a very strong relationship between Nino 3.4 and precipitation anomaly as percent there, but it is stronger in the latter half of the winter, and it's stronger in Southern California than Northern California. But if you look when we get to Nino 3.4 values of the type that we're expecting for throughout this winter, there's really almost no, in the historical record, there's no event of that strength that has gone along with below normal precipitation. In fact, in the south, they've all gone along in upper tercile distribution, same in the north. The vertical orange line there is what the forecast, dynamical model average forecast SST anomalies are, and they're off the range of what we have seen there. So, because it's impossible to say that there's such a small sample size what will happen, but based on the historical record, it seems to have eliminated the impossibility of even a normal winter and shifted it into very high probability of a wetter than normal winter. Well, how wet is it? The table at the bottom takes the accumulated last 4 winters precipitation anomaly and expresses that as a percentage of climatological normal. So in the Northern California, the 4-winter accumulated deficit is about 150% of normal. And in the Southern California, it's almost 200% of normal. So you would need, in Northern California, 1.5 times the usual amount of precipitation to eliminate the precipitation deficit, but almost twice as much precipitation to eliminate the deficit in Southern California. Wasn't easy to draw those as horizontal lines on these scatter plots because they are levels of precipitation that are above and beyond what has ever happened in the historical record. Okay, so to conclude, I think California is in the 5th year of a roller coaster ride of tropical sea surface temperature driving of winter precipitation. Those deficits, 150% north, 200% south, it's unlikely the precipitation anomalies in this coming winter will be able to eliminate precipitation deficits of that, but we're in a bit of uncharted territory here in terms of El Nino driving of California precipitation. The strong El Nino events tend to make California wet, but more so in the south and in the north and in the late winter than the early winter. So we shouldn't be surprised if we've got through beyond AGU, for example, and we haven't seen any really heavy precipitation in California. It may still be coming, so let's be patient there. Definitely the forecast for a strong El Nino persisting all the way through to the late winter, so that is exactly what California wants if it is going to be wet from south to north. We'd need a record wet, however, to erase the deficit. But we presented this in the Drought Task Force on Friday or Thursday last week, and Randy Costa pointed out, well, you know, that's what's needed to eliminate the precipitation deficit. But to eliminate the drought, we probably don't need all of that because runoff has gone down, evapotranspiration has gone down, and from the user point of view, water use has gone down. So the probably effective drought removal requires a lesser precipitation anomaly than is needed to actually remove the precipitation deficit. The only other point I'd like to make is that, you know, this is purely a California focus here. And of course, we in the United States are very excited about an El Nino event and what it means for California. But colleagues Solomon Shang and Kyle Meng published an editorial in The Guardian a few days ago pointing out that although there's so much focus on the El Nino for California, but throughout the tropics, this is very bad news. The title of their editorial was something like El Nino, Save California, Destroy the Tropics. So at the same time we're salivating about a wet winter in California, droughts throughout the tropics, Indonesia, Africa, the Amazon, let's not forget that because this could be a devastating event in other tropical parts of the world. Thank you.
Thank you, Richard. That was really fascinating. We'll open it up for questions. Again, if you're online, you can go to the participants menu and then hit the hand button or use Q&A or send me a chat message. Anyone in the room here have a question for Richard? Okay, let's see. There is one question here in the chat, Richard, from Eleanor Martin. The question is, could you comment on the role of rain versus snow in the forecast for California? Will increased precipitation necessarily rebuild the snowpack in the mountains?
Well, we didn't actually look at that. I haven't actually heard anything about that. I don't know whether any of our colleagues anywhere have looked specifically into these forecasts as to whether what they're predicting in terms of snow as opposed to rain.
I don't know, John, do you have any comment on that, if you're still there?
I'm not sure. I haven't looked at that.
Okay. Well, thanks, Richard, for taking a hack at it. I'm also wondering, do you have any initial ideas why there's this lag between the, El Nino peak temperature and the precipitation atmospheric response over the West Coast? Do you have an initial kind of concept of why that might be happening?
Well, we of course actually put in a letter of intent to your program, and it was just about that, and it was discouraged. So we're not putting in a proposal about it, but we do have some ideas about. One, I think it might be the delayed warming of the tropics that's causing the whole tropics to warm up with a delay behind peak Nino 3-4 temperatures. I also think it's possible that the basic state in the tropics are changing such that the anomalies are occurring. The later in the winter, they're occurring on a warmer mean temperature in the tropical Pacific. And the other idea is it actually takes quite a lot of months for the interaction between the storm track and the stationary wave to play out and operate in a positive feedback, so that for purely dynamical reasons, the teleconnection can strengthen as the winter goes on. But certainly I think from the developing the seasonal predictability, that's going to be interesting. I find it a very fascinating dynamical problem to work on. So hopefully we'll find some way to look into that.
Yes. There are a couple other questions here rolling in. So this is from, Jack Settlemeyer. This question is, I see your strong El Nino years are different than those that John showed. I assume you use a different Nino region to define your strong events? So that's the question. Do you use a different Nino region to define your strong events, or is it 3-4?
We use Nino 3.4, and the two strongest were 82, 83, and 97, 98. Apart from that, maybe there's some difference about what the base period is that's used to define the strong events.
Yeah. There are a number of questions, and we probably don't have time for all of them, but the next one's from Rong Fu. Rong asks, you also show higher SST anomalies in the tropical Atlantic, which could contribute to drought over the American West. Could warmer SST anomalies over the tropical Atlantic contribute to droughts over California in late winter?
I suppose they could do, but I would imagine, from what I'm aware of, I think the tropical Atlantic tends to play more of a role for North American drought in the summer half of the year than in the winter half of the year. I think when we have an El Nino event of this strength going on, it's almost certainly to be by far the most dominant influence on winter precipitation at the West Coast.
Okay. Thanks. Then we'll take one more. This is from John Brown. John, are you on the line?
Yes, I am.
Okay, go ahead.
I just wanted to make a comment about snow in the mountains. Somebody asked about that. I'm not a climate person, but I'm a native Californian, and I follow things quite closely. The tendency is in El Nino years for the trajectory of the low-level air to be more from the west-southwest than the west-northwest, as is oftentimes more typical in other years. And with the warm sea surface temperature anomalies offshore right now, I would expect that the wet bulb potential temperature of the air that's coming in and going to be bearing the precipitation is going to be somewhat warmer than typical. So snow levels would be higher. So the high mountains would benefit, but below, say, 5,000 feet or 6,000 feet, they may not.
Okay, thanks for the comment, John. Thanks for the presentation, Richard.
Oh.
Okay, so next up is Andy Hole. Andy, are you on the line?
Yes, I'm on the line.
Okay, great. So I'm switching control over to your computer.
Okay.
Just share your screen with us.
Absolutely.
So do you see the screen?
No, not yet. You have to share your desktop with us.
Okay. Does anybody see where that button is?
No, now you can.
But I did say it. I said it.
Share.
So if you're in WebEx, you can go to the Share menu at the top
Go to the top. Right there.
and then click My Desktop.
All right.
Okay, great.
Good. Looks like we're in. Okay, so this is
And then, and Andy, if you can just swap displays,
Oh,
because we're seeing your notes right now.
right. There it is, finally.
Great, okay, thanks a lot.
All right, good, here we go. All right, so this is a team-wide collaboration across our group at the Earth System Research Laboratory. And this is part of our effort for ENSO and El Nino situational awareness in terms of the impacts over California and the western United States. So considering the current California drought and the forecast El Nino, we pose the question, does El Nino intensity matter for California precipitation? So I'll begin here with an analysis that shows that California rainfall during El Nino is mixed, and this dovetails what Richard showed previously. So what the plot shows here is California precipitation for November through April, 1896 to 2014, and this is a percent of the long-term climatology. This is statewide precipitation from the California, from the U.S. divisional data set. The stars here on the plots show El Nino seasons, moderate to strong, our definition that I'll define in a couple of slides from now. And there are 16 such events that we've defined. And the arrow right here shows the two very strong El Nino events, and those were 1982 to 83 and 1997 to 1998. So aside from the fact that California precipitation goes through these long-term, drought and wet periods, we see that California precipitation during the moderate to strong El Nino events is fairly mixed. So for 8 events, there was below average precipitation, November through April precipitation, and then for 8 of the other events, there was above average precipitation. During the very strong California, those very strong El Nino events, California precipitation was above average, and in fact, 2 of the 3 top California precipitation seasons from November through April occurred during those very strong El Nino events. So to address the central question that serves as our title, we pose 3 additional questions in light of what we saw on the previous slide. So the first question is, statewide California precipitation, wet, symptomatic of a sensitivity to sea surface temperature forcing during very strong El Nino. And I'll use the notation VS as a very strong El Nino. And the second question is there a difference in the impacts of very strong El Nino and moderate to strong El Nino? And MS serves as our acronym for the moderate to strong El Nino. And then finally, how do the risks for wet versus dry rainy season conditions change with El Nino? Here's a slide for our observed data sets here. And the top point here is that our observed precipitation was drawn from the U.S. Climate Division data set from the Vos et al. 2014. And then sea surface temperatures were drawn from the Harrell 2008 data set. That's the merged Hadley OI data set. And this was used to define our El Nino events and additionally to show what sea surface temperature composites or average composites during our El Nino events. And since we only have a few samples of El Nino events, and especially those very strong El Nino events, we use model simulations driven by observed historical conditions to test the effect of the El Ninos. So the models were driven by observed monthly time-varying sea surface temperatures, sea ice, greenhouse gases, and ozone, and the period for this is 1979 to 2014. We used 3 models here, and those 3 models were CAM5, GFS version 2, and ECM5. And for all of those models, we have 130 ensemble members. And since all of those models simulate similar California precipitation during November through April, we aggregated all those ensembles into one super ensemble. So the results that I'll show in the following slides reflect that of the super ensemble. So ENSO events were defined using the Nino 3.4 index centered on the December, January, February season, and the base period is for 1896 to 2014. The definition of our very strong El Nino events was for a Nino 3.4 index to have greater than a 2 Celsius anomaly, and our moderate to strong events fell between a 1 Celsius and 2 Celsius anomaly for the Nino 3.4 index. So in the table right here, I list the January of each of those seasons. So the very strong El Nino events, of course, were 82, 83, and 1997, 1998, and the moderate to strong El Nino events are listed below. For the model simulations, those analyses, those only incorporate 1979 onward, whereas the observed plots that I'll show incorporate that entire period. So the purpose of this slide is to show that sea surface temperature anomalies during the very strong El Niños and the moderate to strong El Niños are quite different. So the left-hand plot shows the very strong El Nino SST anomaly composite, and it's very clear that these two events really stood out from the others in that there was a very strong sea surface temperature anomaly that extended from the central and into the eastern Pacific Ocean. Whereas the SST anomaly composite for the moderate to strong events for November through April were much, much weaker, and the strongest SST anomalies within that actually fell within the Nino 3.4 region, just east of the dateline. So the purpose of this slide and the following slide is to show that strong regional rainfall changes occurred during El Niños, or specifically during very strong El Niños. What these plots up top show are the observed precipitation during very strong El Niños and the moderate to strong El Niños. And what I want to point out here is that this is done in the climate division level. So the thin lines show the California climate divisions. These thick lines show our definition of North, Central, and South California that we'll use for the following analyses. So North California incorporates climate divisions 1, 2, and 3 for California. Central is climate division 4 and 5, and Southern California incorporates climate divisions 6 and 7. So during the very strong El Nino events, there was a statewide wet condition in excess of 150% of average during the very strong El Niños. Whereas for the moderate to strong El Niños, and those 16 events from 1896 to 2014 only show or demonstrate a sensitivity to those El Nino sea surface temperatures over Southern California. And those values were about 120 to 130% of average. So since there's so few samples, especially for that of the very strong El Nino events, we use the 130 model simulations to test the precipitation response to the El Nino. So we introduced that down below here in the simulated precipitation. So on the left here is the very strong El Nino events. On the right here is the moderate to strong El Nino events. And again, we see a really close correspondence between the precipitation, the simulated precipitation, and the observed precipitation. So specifically, we see a very strong sensitivity to the sea surface temperature anomalies over Southern and Central California. We also see a very strong signal over Northern California of about 130 to 140% of average. When we look at the moderate to strong El Nino events, there's a very close correspondence to observation. The only thing that really stands out here, or that's different between the simulated and observed, is over this climate division number 5. And it's actually very close here. This climate division is about 112% of average, so it just meets the contour interval here. But otherwise, the plots are very similar. So the takeaway from this is that North and Central California are sensitive to the very strong El Niños only. So this picture right here is, we show the same plot as in the previous slide, but we back out a little bit, and we show a larger domain that includes much of the western United States to show the close correspondence between the models and observations. And again, we see these strong regional changes associated with the very strong El Niños. And in particular, the southwestern United States is more sensitive to the very strong El Nino events in models and in observations as they are to the moderate to strong El Nino events. And this again is for November through April precipitation during El Nino. So in this slide and the following slide, we'll assess the change in regional precipitation using probability distribution functions of November through April precipitation. So PDFs, like we've done in everything here, this is a percent of ENSO neutral. What we've done here is we've shown these in terms of ENSO neutral as to not allow the El Nino events to actually bias what's going on here. So specifically, this is for Northern California. And this red line right here is the modeled response to the very strong El Nino events. The orange line here is the modeled response to the moderate to strong El Nino events. The black line right here is the observed response to the moderate to strong El Nino events, and the green line is ENSO neutral. Real takeaway from this plot right here is that there's a shift toward wet conditions over Northern California during very strong El Nino events that we don't see in the moderate to strong El Nino events. Also, what we see is there's a lot of similarity between the moderate to strong El Nino events in observations and in the models, and there's not much of a change relative to the ENSO neutral. Now this slide right here, what we do is we introduce the Central and Southern California PDFs. So right here is Central, and in the bottom panel right here is in the South. So the Central California PDF tells a pretty similar story to that of Northern California, in which during very strong El Nino events, what we see is a slide toward wet conditions over Central California during very strong El Ninos. Whereas during moderate to strong El Ninos in both models and observations, we don't see that shift toward wet conditions. Both the observation and the modeled response to moderate to strong El Ninos are very similar, and they have a lot of similarity here to the ENSO neutral conditions. Now for Southern California demonstrates a sensitivity to very strong El Ninos in addition to the moderate to strong El Ninos. So over Southern California, there's a shift toward wet conditions during the very strong El Ninos, shown here in the red. And there's also a shift toward wet conditions during the moderate to strong El Ninos as well. And this is also seen in the observed response to the moderate to strong El Ninos. Now again, here's the ENSO neutral line, and the ENSO neutral line is just pretty Gaussian and close to the average. So the real takeaway from this is that there's an overall shift to statewide wet conditions during very strong El Ninos in North, Central, and South California. Now this plot right here, it shows the change in the regional precipitation probability during very strong and moderate to strong El Ninos using cumulative distribution functions. The notation here is the same as the notation in the previous slide with the PDFs. So again, the red line shows the modeled response to very strong El Ninos. The orange line will show us the moderate to strong El Nino response in models, and the black line right here shows us the response, the observed response to the moderate to strong El Ninos. Or Northern California, and this shows a similar picture to the PDFs, in that we see a very shift toward wet conditions over Northern California associated with very strong El Nino events. The way to read this right here is anything to the probability is shown at anything to the left of this line. So what the model simulations show us here is that there's only a 5% chance in Northern California that precipitation is below average. And we've looked at this across each model. In each model, the reason why we felt very comfortable in putting together a multi-model ensemble was because each model simulates similar regional precipitation. And we can show this in terms of the CDFs, what we're showing here, and in terms of the PDFs that I showed in the previous two slides. And we see a similar picture over Central California as well, that shift toward wet conditions, and also a very small probability, less than 5%, that we will see below average precipitation, or that we see below average precipitation during the very strong El Nino events over Central California. And the same thing can be shown over Southern California as well. Now there's a very strong, because of this rightward shift or this wet shift in the distributions over North, Central, and Southern California, what Richard was showing before is that Some people are saying that we might need 200% of average or 150% of average in order to make up for the precipitation deficits that we saw over the last 4 years. And what these plots here show is that there's a non-zero probability and there's an enhanced probability relative to the ENSO neutral conditions and the moderate to strong conditions that we will see, that we can see that during very strong El Nino events. This plot right here shows the change in precipitation during very strong El Nino events as partitioned by each month of November through April. So this is the precipitation percent of ENSO neutral, and the shading corresponds to a probability of less than 0.05. So these are statistically significant, this shading here in the plot. And the takeaway from here is that during very strong El Nino events in these model simulations is that there's a mid-season maximum during the very strong El Nino events. Specifically, during January, February, and March, we see the largest amount of precipitation during these very strong El Nino events. And Richard touched on this before, that there's this mid-season maximum. So if we don't see precipitation ramp up over California during November and December, there really isn't that much of it shouldn't be that much of a concern in terms of where the precipitation begins during the season. Now, during moderate to strong El Nino events, we actually see a little bit of a different story. During the moderate to strong El Nino events, there is a late season maximum of precipitation. So again, this is a modeled result, and this is showing precipitation percent of ENSO neutral conditions. So early in the season, November, December, January, the models tend to prefer wet conditions, especially over Southern California. But really during February, March, and April, there's more of a preference in these model simulations that the precipitation becomes wetter during the late part of the season. So as a means to conclude here, I'll just return to our questions that we posed initially. So the first question is statewide California November through April wet symptomatic of a sensitivity to sea surface temperature forcing during very strong El Nino? And the result that we found was yes. Very strong El Nino forces precipitation in excess of 130% of average over all climate divisions of California. Our second question, is there a difference in impacts of very strong El Nino and moderate to strong El Nino? So what we found is yes, North and Central California are sensitive only to very strong El Nino. And then finally, how did risks for wet versus dry rainy season conditions, that's November through April, change with El Nino? And what we found is that very strong El Nino nearly eliminates the odds of below average November through April precipitation. So that concludes. Thank you.
Okay, great. Thanks a lot, Andy. If you're online, again, use the participants hand raise feature or Q&A or chat if you want to send a question for Andy. Any questions here in the room for Andy?
I have a question. This is Heather Eschenbaugh at CPO. Have you looked, or Richard or anyone else, at the role of the Arctic oscillation? Is it equally likely to be in a negative phase versus positive phase when you have these strong ENSO events? Or can you comment on that in general?
As it pertains to the Arctic, not quite sure. I personally didn't look at that. I don't know if anybody here in the room looked at that.
Just observationally, this is Klaus Walter. Observationally, 82, 83, and 97, 98 were mostly positive NAO, AO. I think February 83 it flipped for 1 month, but otherwise the observational record is pretty clear that you don't necessarily get a negative AO. It looks like it's more comfortable with a positive AO.
Thanks.
Okay, thanks for the question, Heather. So I'm not seeing any other questions here. Any other questions here? Yeah, Ken.
I noticed that you said you drove your model with SST, greenhouse gases, and ozone. Did you see any impact of the greenhouse gas and ozone?
On a specific season or on the
any
very
impact
strong?
At all? I mean, I noticed you emphasized that ozone and greenhouse gases were inputs to the model.
Right. Well, we have to state that for full disclosure, but specifically looking at the effect of greenhouse gases on the events we listed here, no.
So you didn't look for it?
No.
Okay, thanks, Ken. I see there's also a question from Lifang Luo. Lifang, are you on the line?
Yes.
Okay, great. Go ahead.
Hi, this is Li Fengluo from Michigan State. I have a question for Andy and Richard. If I remember correctly, in Richard's presentation, he talked about how strong El Nino and precipitation anomaly the associated precipitation. Looks like with strong El Nino in Richard's presentation, the precipitation is happening at late season, and that's different from what Andy shows in his analysis. I mean, if I remember correctly, can you guys comment on that?
Well, I don't think we're necessarily showing different things. Richard broke it down into DJF and FMA, and I think we're showing very similar things here. And I'm going back to one of our slides where I show the monthly breakdown. And I have to swap displays. So Richard's seeing an FMA maximum, and I think we're seeing that as well, where it's in these model simulations more heavily loaded toward the response during February and March than it is during April. So I don't think there's much of a difference than what Richard was presenting.
Okay, thanks for the question, Li Feng. And I think we're a little bit past 2, so we'll conclude the webinar now. Thanks to the 3 speakers. It was a very interesting series of talks. A pretty large audience online, so I know there's a lot of interest in this topic. So thanks for taking the time to put these slides together and present today. And thanks for the audience, all the interest in this webinar. A recording of this webinar and the slides will be up on our website probably in the next 24 hours. And we're going to continue with the webinar series in October. We're still working on planning out all of the sessions that we're going to have over the next few months. So you can stay tuned to cpo.noaa.gov/map/webinar for updates. And we're looking at topics that include scientific issues with weather, climate timescale, Earth system modeling development, climate predictions and projections related to fisheries, and ensemble prediction, amongst a number of different topics that we're working on. So thanks for attending. I hope that you'll come back for another MAP webinar.